Hey folks, as iOS developers we work a lot with UI. Today we will try to understand how UI actually works under the hood. We will cover both UIKit and SwiftUI, but we'll start with UIKit first and save SwiftUI for the speed. So let's consider an example that often can be seen in UIKit applications. At a certain point in your app, you want to add a subview within view-did-load method of some plain old view controller. Looks pretty trivial, right? But how it actually works? Let's split the bigger how into smaller questions. What happens before we change the UI and view-did-load method? And how the change of UI is applied? How this new subview appears on the screen? First of all, let's start with understanding what happens after we launch the app. The Xcode debugger will be our best friend today. Let's create an empty UIKit Swift project in Xcode and put a breakpoint into view-did-load method. As you probably know, by default you will see something like this on the screenshot, but you can expand the call stack by tapping on the button in the bottom right side of Debug Navigator. We can see here a lot of calls on the main thread. Probably obvious and well-known fact that our UI-related code is happening on the main thread. UIKit is not thread safe, you should work with it on main thread only. But let's look on the bottom of the call stack on the previous screenshot. What we see here is the main function. It is called by the operating system's runtime environment when your app launches. System initializes your app's environment, setting up the app's main thread and then calling the main function, which can be considered as an entry point of your app's execution. For example, if you create an Objective-C project in Xcode, yes, you still can do it, you will see something like this. Just imagine, all that happens inside your app happens inside the main function. So it's fun, but entire app is nothing but a single giant call of main function itself. But main function itself doesn't do much. Its main purpose is to call UI application main function. UI application main function in its turn does a lot to set up our iOS application. It creates the UI application shared instance and application delegate. It runs the UI application that triggers creation of scene delegate, and etc. And last but not least, it runs the main event loop called run loop. Let's update our scheme with a new step. But what is the run loop and why it is so important to our app? Simply speaking, run loop is the infinite cycle of events happening in the app. Run loop is the reason why main and UI application main function calls will actually never return. Every run loop iteration has three main jobs to do: handle the events, notify observers about run loop state changes, and put the thread to a sleep when it have nothing to do. Yes, the run loop is associated with a thread, with only one run loop linked to each thread, and it automatically runs on the main thread from the app setup from UI application main function call. But for other threads, you must explicitly run it. If you place a breakpoint at nearly any line of code of your app, you will likely encounter one of the functions listed below at the bottom of the call stack. These functions serve no purpose other than helping in debugging. Run loop ensures that all main thread code is executed through one of these functions. They also allow you to understand the exact type of event processed by the run loop that triggers the execution of the code where you set the breakpoint. Run loop handles several types of events. You have probably created timer or used GCD main queue, the first two of them. We will discuss sources and observers a bit more. Simply speaking, run loop source is just a way to say to run loop that some event happened at some other point of the app or even in the different process, and run loop should handle this event. As you probably noticed, there are two types of sources, source 0 and source 1. Not really a clear naming in terms of purpose, right? They named so because the version field of the context structure that used to configure the source, it's 0 or 1. But they serve different goals as well. Version 0 sources are for inner app communication, and version 1 sources are for inter-process communication. Version 0 sources managed by the application. It's kind of inner app messaging mechanism. When a source is ready to fire, like some other part of the application, perhaps code on the separate thread, must call cf runLoop source signal method to tell the runLoop that the source is ready to fire, so the related callback can be called. Good example for version 0 source is UI events fetching. If you put a breakpoint in the UI button tab selector, you will notice that UI event that triggered this action was fetched using version 0 source. Version 1 source is managed by the kernel. The sources use MAC ports to signal when the sources are ready to fire. The source is automatically signaled by the kernel when the message arrives on the source's MAC port. MAC ports are primarily mechanism for inter-process communication, or IPC, within the macOS and iOS operating systems. They allow processes, and our app is one of them, to send messages and data between each other. For example, version 1 source is used under the hood of CA display link. CA display link often used to synchronize your code to the display refresh rate. runLoop also has observers to notify when runLoop state has changed to the one of those that you can see here. You probably will never need to create runLoop observers in your app, but being aware of the existence and purpose of runLoop observers can be useful for understanding how UIKit works under the hood. But before we will try to understand connection between runLoop observers and UIKit, we need to understand what is hidden behind the UIKit. Core Animation is a lower-level framework that lies under the hood of UIKit, and is responsible for many aspects of UI and animation. We use UIKit every day to create UI in our apps. UIKit contains all kinds of components, but surprisingly UIKit delegates a significant portion of UI-related tasks such as animations, layout and rendering to Core Animation under the hood. Core Animation actually do so much work related to UI that the best book about UIKit is actually the book about Core Animation. It's iOS Core Animation Advanced Techniques by Nick Lockwood. It was published back in 2013, but it's still relevant if you want to master UIKit. First important thing about UIKit and Core Animation connection is that behind every UI view hides a CA layer. When UI view is created, it creates CA layer under the hood and sets itself as a CA layer delegate, which is responsible for several things, such as providing the layer's content, subviews layout, and animating property changes. For example, UI view is actually the reason why UI view properties are not animated by default, opposite to CA layer. UI view disabled default animations as a CA layer delegate to its layer. Properties and methods of UI view that somehow change the view appearance are actually just proxied properties of CA layer. For example, frame, bounce, background color, or isHidden properties are actually proxied properties of CA layer. The several things that truly handled by UIKit itself are user interaction like touches and gestures and accessibility. Views on the screen together create the view hierarchy or view tree. And under every view we have a layer, so there should be a layer tree hierarchy in the app behind view tree. But surprisingly, there are 3 layer trees out there. Model layer tree, or simply layer tree, presentation layer tree, and render tree. Each layer tree has a different role in making the content of your app appear on screen. Model layer tree, or simply layer tree, is the one your app interacts with the most. The objects of this tree are the model objects that store the target final state values for any animation. Whenever you change the property of a layer, you use one of those objects. Presentation tree contains the in-flight values for any running animations. Values are only an approximation for the state of the screen, so presentation tree is sometimes called ghost tree because of that. Render tree performs the actual animations and it's private to core animation. It's the most closest tree to the actual on-screen state. But how changes of the layer tree are applied to the render tree? It's a good question. UI changes are not applied to be updated on the screen every time something is changed. Core animation groups the changes of layer tree into CA transaction, a mechanism for grouping multiple layer tree operations into atomic updates to the render tree. But when and how this transaction takes place? Do you remember run loop observer events I mentioned earlier? Core animation observes one of those events of run loop state. It's run loop before waiting event. When this event fires at the end of every run loop iteration, core animation initiates the UI update by committing the CA transaction with all changes to the layer tree grouped together made since last UI update. If you put a breakpoint in the layout subviews method of your view, you will see that it is called from runLoopObserver callback function by discovering corresponding function on the call stack. Let's update our scheme with a new step. So, UI is updated during each run loop iteration, if something needs to be updated, of course. If there is no changes to layer tree, no transaction is created. This transaction is called implicit transaction because we don't create it manually. Let's update our scheme with a new step. To understand CA transaction better, let's consider an example. Let's imagine we have a button with background color initially set to red. When we tap on button, we change the background color to yellow, block the main thread for 3 seconds with sleep function, and change the background color to green. If you run this example, why the yellow color isn't visible? It's because despite setting the yellow color and changing the model layer tree, we blocked the main thread, suspending the current run loop iteration. So the implicit transaction was begun but wasn't committed until the 3-second interval had expired. However, immediately after this 3 seconds, we changed the color to green, and this green change was committed with the implicit transaction at the run loop cycle's end. So the yellow color change never became visible. I mentioned earlier that core animation sends implicit transaction on every run loop iteration, but transaction can be also explicit if you create it in your code like this. Under the hood, CI transaction begin and commit manipulate a shared transaction stack maintained by core animation. When you call CI transaction point begin, a new transaction object is created and pushed into transaction stack. Any changes made to layer properties between CI transaction begin and commit are grouped together and committed automatically together. Now we see yellow color state, right? But why? It's because we committed the yellow state change with explicit transaction right before blocking the main thread, so it was changed instantly after the tap. Then, after 3 seconds, we see green state change that goes with implicit transaction at the end of the run loop cycle. Let's consider a third example. As you can see, it produces the same result as the first one. No yellow state appeared. That occurred because transactions can be nested. When one transaction is nested with another, the commit of the internal child transaction only takes effect when the parent commits. To understand better why nested transactions function this way, consider that transactions are managed by a shared transaction stack. Last in, first out. When you begin a transaction, it's added to the transaction stack, and on committing, it's removed. Nested transactions will only be committed to be applied to the render tree when the stack becomes empty. Last example shows us how implicit transaction works. Looks very similar to the example with explicit transaction when yellow state was visible, except one important detail. We changed the model layer tree first by assigning background color to white, which triggered implicit transaction to begin. So our explicit transaction was nested into implicit one and was not sent to the render tree until the implicit one was committed later. So we saw only green state after 3 seconds in this case as well. There are 4 phases of transaction. It's layout, display, prepare, and commit phases. All of them are actually happening inside CA transaction commit method. We can see this method inside the call stack if we put a breakpoint inside layout subuse method of your view. You can also see CA layer layout and display if needed method in the call stack. It's responsible for executing 2 phases, layout and display. Layout phase handles the layout update of the layer tree before the transaction is committed. Similarly, the display phase is responsible for updating the displayed contents within the layers. Core animation initiates these phases before committing the transaction to ensure the layer tree's state is up to date and can be applied accurately to the render tree. Both phases function in a similar manner. Core animation traverses the layer tree using depth first search or DFS, starting from the top super view, its UI window, down to the bottom leaf layers. If the layer's corresponding flag, returned by needs layout or needs display, is activated, the layout sublayers or display methods are called accordingly. These flags can be activated implicitly by modifying the layer's properties, such as bounds, for instance, or explicitly by invoking setNeedsLayout or setNeedsDisplay methods. For better understanding, let's have an example. If the entire layer tree is invalidated using setNeedsLayout during the traversal in the layout phase, layout subviews will be invoked for every layer, but most of the time tree is invalidated only partially. In that case, layer tree will be fully traversed too, but layout sublayers will be called only for invalidated layers. Let's start with layout phase. You probably remember layout if needed and setNeedsLayout method of the UI view. But they both serve as proxies for the corresponding methods of CA layer. Of course, UIKit adds additional logic there to ensure the proper functioning of after layout constraints, but it consistently depends on core animation, fundamental layout process. Default implementation of layers layout sublayers calls the layout sublayers method of the layers delegate object if it's implemented. As we mentioned above, UI view sets itself as a CA layer delegate of its backing layer. UI view implements layout sublayers method of the delegate and calls UI view layout subviews method inside it. Layout subviews is meant to help UIKit to support auto layout, and it adds one additional step to layout phase, constraints pass. This is the step UIKit does to solve constraints. It goes over the view tree bottom up from leaf subviews to the root view and calls update constraints method of the view. If needs update constraints returns true. It usually becomes true automatically when constraints were changed or if you call setNeedsUpdate constraints explicitly. Let's move to display phase. On this phase, core animation invokes the display method of each layer within the current layer tree, proceeding from top to bottom, from super to sub layers. This method is responsible for updating the layer's content. By the end of this phase, every layer has its content refreshed. Subclasses have the option to override the display method, utilizing it to directly set the layer's content property. The mechanism involving setNeedsDisplay and needsDisplay is the same as for layout phase. This is more precise scheme of how display phase works. Understanding it all at once can be challenging. But the most crucial aspect here is that UIKit empowers us to perform custom drawing using core graphics by overriding the drawRect method in the end. You can use drawRect method to draw custom graphics like lines or shapes in the core graphic context. It's usually used to draw custom components. For example, you can draw 100 ellipses to see a torus like this. But that's not the only case. For example, UIKit uses drawRect to draw the text in the UI label. It calls drawText in Rect method there. You can override drawRect method of label without calling supers method inside, and you see no text drawn in the end. Okay, now we know that committing transaction triggers layout and display phases to happen. Say transaction actually has two more phases. Usually developers don't interact with them, but they are important because of what they do. Prepare phase does additional core animation work like image decoding and image conversion. Commit phase packages up layer tree and sends the transaction to the render server to be applied to the render tree. Now you probably noticed a new keyword here, render server. Until this moment, we didn't discuss where exactly render tree is located. And surprisingly, not in our app. Render tree is managed by a separate process called render server that issues drawing calls for the GPU using Metal. This process performs most of the magic of the core animation framework. Maybe you were wondering when you debug your application in the Xcode why progress indicator is continuing to spin, even though your application is paused. Now you know why. It's actually spinning in another process. It will happen with any other animation as well. If you commit the transaction with animation added before you block your main thread, you will see how it continues to work. Once render server receives the transaction, it decodes it to apply updates to render tree. For every display update iteration, render server needs to provide next frame to the GPU, so it does the following. It calculates the intermediate values for the render tree's layers properties if related animation is in progress. It uses the metal commands to perform the layer tree rendering. The output of rendering on GPU is a pixel bitmap to be shown on the screen. Let's recap everything. UI application main function manages the app setup and runs the main event loop. Main event loop or run loop is infinite cycle managing app events. It handles events like GCD main queue blocks, timers, sources, and observers. UIKit internally delegates UI-related work to core animation. UI views are backed by ACA layers, handling rendering, layout, and animations. Core animation holds in parallel 3 layer trees: model tree, presentation tree, and render tree. Core animation renders our app layer hierarchy at each run loop pass, but not at each layer modification. To do so, as an observer of the run loop, core animation commits say transaction just before the thread is put to sleep, if any modification were applied to any layer. Say transaction is core animation's tool for combining multiple layer tree operation into atomic updates to the render tree. Explicit transaction can be created manually with begin and commit methods, and they allow immediate change commits within the transaction scope. Transactions can also be nested, but when nested within ongoing transaction, changes with the nested one only commit when the parent transaction does. transaction consists of 4 phases: layout, display, prepare, and commit. At the end of every run loop iteration, core animation commits implicit CA transaction through inter-process communication to another process called render server. Render server is a separate process that manages the render tree and is responsible for animations and rendering. It uses the metal commands to perform the rendering. Metal commands will be translated in the corresponding hardware commands, and output of rendering on GPU is a pixel bitmap to be shown on the screen. Thank you for your time, and see you in the next videos.